in 10.1?
Yeah.
Okay.
These are interesting.
I know.
Happy days.
Yeah, that's the one I was talking about, yeah. Okay. Oh boy. Here we go. 39. So the particle travels clockwise around a circle. Center of the origin, radius 5, completes a revolution in 4 pi seconds. So how long does it normally take? If I have, yeah. And the seconds thing is because we think of t as a time, yes? So what is the normal period for sine theta? 2 pi. Does anyone remember how to make the period become twice? Because that's what I need to do here, yes? Make the period become twice as long as it was? Yes. But you're leaving. I'm like, all right. Damn, I keep saying something to offend people and they leave. You and your math. So if I have sine theta, that's got a period of 2 pi. So if I put sine theta over 2, that now has a period of 2 pi over k, 2 pi over 1/2, so I get 4 pi. Does that look at all familiar? And again, if the same people, it doesn't look familiar to you, I'm going to go find your pre-calc teacher and just slap them one. Maybe it's been a while. Maybe it's not their fault. I don't know. So one part of this problem is, how do I create it so it has that period? That's all you have to do there. So for us, it's going to be a t here, yes? To make it all parametric instead of polar. What was the other part of this? It had to go clockwise?
Yeah.
Yeah, so, and it's got to have a radius of 5. Radius of 5 is easy. Clockwise is interesting. So I'm not gonna do a lot with this. I need you to play around with this thing. Normally, what way am I gonna go? If you start throwing stuff into sine and cosine,
Counterclockwise.
yeah, counterclockwise. So now you just gotta figure out, how do I make this thing go clockwise instead? I don't know. Start playing around with it, yeah. But you see what I mean? This is the step. I don't want to do too much because it's all about you playing around with it. Take a guess, throw a negative in, and see what happens. And you have your calculators. You just plug it in the calculator so you're not like trying to graph every little change you make, right? Every breath you take, every cake you bake, I will be watching. Nobody knows this on here. Is that okay? Is that better? So that's all about playing around with it to make those things happen. This was more of a direct trigonometry idea. How do I change the period? Right? Does that sound familiar at all? That K letter, does that trigger anything? You had to do the amplitude, the phase shift, get the K so you can figure out the new period. Concerned about it. If you took trigonometry, yes?
Yeah.
Okay. Sounds like they just left chunks. Did you take it during the pandemic? I don't mean to focus on you, I'm sorry. Huh?
I believe so.
Ah, okay. So that could explain some things. There were definitely holes in pandemic classes. Okay. Anything else from homework or generally? Okay. So let's do this. Let's get into this stuff. And I want to give you this paper. And actually, before I give you this paper, it's hard to do that without giving you this paper. Damn it. All right, let's just do this. Wait, hold on. Before I give you this paper, because it's got too much information on it right now. Let's say I have this equation. Right, and you're an insane teacher that expects you to know all of mathematics all at once. He wants you to do this by hand. He I want you to graph this thing by hand. Right? Because somebody in his past hurt him, and now he wants to take it out on a random group of people, different group of people every semester. I get to torture them. So, how would you start doing that? I want the graph of that, and I want you to do it by hand. As soon as you might remember what it looks like, but let's pretend like we don't. But when you first learned how to graph y equals x squared plus 7, what did you create? A table, yes. So I'm going to create an r theta table, which is still backwards, but too bad for me. And the great thing about trig functions is very often you get to a point, they just start to repeat. So even if they don't give you a range of values, you're just going to go until it kind of like lines back up with itself. And then you're like, okay, it's going to keep doing that forever. Will it always happen? No. Will it most of the time happen? Yes. So tell me what to shove it in for theta first. 0, holy shit, yes. So when you put a 0 in, what's cosine 0? 1, so twice that. Holy shit, we're off. We're going. What's the good next thing to plug in because your crazy ass math teacher wants you to do this fully by hand? At least pi over 4. Get a little better resolution, yes? Take too big of a step. You're going to have a graph like, it's not going to be good enough resolution. At the very least, pi over 4. In fact, leave a little room, just in case. What's cosine of pi over 4? Root 2 over 2 times 2. Root 2, and root 2 is approximately 0.7. No, I'm doing root 2 over 2. Root 2 is approximately 1.4. Not 0.7. Don't divide it. It's really good just to know root 2 is about 1.414. Or not. You don't have to. Yes? Oh, yeah, that one I turned around. Of course I did. Let me start over. So 0 gives me 2, pi over 4 gives me 1.4. Thank you. And now, of course, I'll do like you guys said a minute ago. Pi over 2. What's cosine of pi over 2? 0. And then if I go to 3 pi over 4, what happens to cosine? Negative, and it just starts repeating itself, yes? So then if I put pi, I get negative 2. I just start repeating myself, yes? Just the negatives of those values, yes? All right, let's graph what we got so far. So I know we don't have polar paper, so we're going to make our own little polar paper real quick. And that's all we need. So if I look at 0 degrees, I'm going to go out 2. Bam. If I look at pi over 4, I'm going to go out 1.4. You with me? If I look at pi over 2, I'm going to go out 0. If I look at 3 pi over 4, I'm going to go out negative 1.4. And if I look at pi, I'm going to go negative 2. That's not supposed to be a point there, Jeff. Oh, I'm looking. I jumped way ahead. Oh, I'm doing great tonight. I am so tired. 3 pi over 4 is here, Jeff. Ignore those. So if I look at 3 pi over 4, I go... Now here's where things get interesting. Okay, here's where I got to be careful. So I'm looking at 3 pi over 4, yeah? And I'm supposed to go where? Negative 1.4. So I kind of like rotated that whole thing. So negative 1.4. And if I look at pi, I'm going to go negative 2. So what I end up with is potentially I need a little more resolution. If I put like pi over, it doesn't really matter. Let's do pi over 6. That would be here instead of pi over 3 over here. Does anyone remember what cosine of pi over 6 is?
Yeah, root 3 over 2. So then root 3 over 2 times 2 is root 3. Square root of 3, I believe, is about 1.8. I think 1.7 something. So if I look at 30 degrees, I should go out 1.8. So then that kind of tells me, okay, it's going to repeat all that stuff. So it's going to go like that. And you guys should remember that cosine leads to a circle on the x-axis. This one happens to have a radius. Now this is really interesting. What's the radius of that circle? 1. 2 is actually the total distance from one side to the other. Yeah. So let's do this. I wanted to do at least a little bit, and this is kind of gross because it's all in graph paper that we kind of made ourselves. So let me give you some graph paper. Do you have, oh, you.
Yep.
So when I got to here, and I do apologize, I appreciate, please call me out whenever I make a mistake. If I face 3 pi over 4, yes, so I'm going to face 3 pi over 4, yes?
Mm-hmm.
Which way, how much am I moving? As I look at that, I'm going to move back 1.4. Yeah. Okay. So here, don't look at that side. There's nothing on that side. Don't worry about that side. Really didn't format this well, but that's okay, Jeff. You'll be fine. Let's use one of these at the bottom because then I got some room underneath it. I want to do one more by hand with you guys. Let's do this one because it gets a little more interesting. Let's do cosine of 2 theta. So that's very different. So if I do that, oops, that should be R. R equals cosine 2 theta. Let's see what we can do here. So if I put a 0 in, now here's where we got to be a little more careful because I'm going to double all my inputs, right? But I mean 0, you're fine. But I have to kind of keep an eye on my inputs because I know I'm going to double them. So what do I get when I put a 0 in? Jeff, you're awesome, Jeff. 0. What do I get when I put a 0 in for theta? Huh? Yes, 1. Oh, I like it. Okay. Now, let me see if you guys. How do I end up evaluating this at pi over 4? What would I plug in? Pi over 2, when I double it, it would be pi. How do I make the inside pi over 4? What do I actually have to plug in? Pi over 8. Because the first thing this thing does is doubles any input. Yes? So we're going to put, and I'm even going to put it in the right place. That'd be amazing, Jeff. Pi over 8. So then I actually end up getting cosine of pi over 4. Yeah, root 2 over 2, which we now know is 0.7.
If I ever make you do these by hand, you only have to go out 1 decimal, because if you are able to graph a difference in the second decimal place, dude, I can barely handle whole numbers. Are you kidding me? Okay, so what's the next thing that kind of makes sense to plug in then? Yeah, pi over 4. And what does cosine actually see? Pi over 2, so cosine of pi over 2 is 0. Now you're going to plug in, let's plug in what? Huh? Yeah, we can, okay, I love it. 3 pi over 8. So if you notice, what we're really doing is no pi over 8, 1 pi over 8, 2 pi over 8, now we can do 3 pi over 8. Since the first thing I'm doing is doubling all my inputs, I could put the over 8 stuff in, because then they become the over 4. Those are angles I know. What is the cosine of 3 pi over 4? Yes, so it'll be negative 0.7. Root 2 is 1.414, this, so cut that in half and you get 0.7, roughly. I don't blame you for not trusting me. All right, let's kind of keep going. I got to make another little dude to keep this going. So 1 pi over 8, 2 pi over 8, 3 pi over 8, 4 pi over 8. And what does it see? What does it actually see inside now? Pi. So what's cosine of pi? Negative 1. No pi. 1, 2, 3, 4, 5 pi over 8. So now it's going to see 5 pi over 4. It's still some kind of 0.7, yes, because it's still like a 45-degree reference angle, but what quadrant is 5 pi over 4 in? Third, so it's still going to be negative. And the nice thing is, you don't have to think anymore now. 1.70, negative 0.7, negative 1. So now it's going to start going back. Negative 0.7. What do I get if I put 6 pi over 8 in? Which is 3 pi over 4. It'll see 3 pi over 2. And what is it there? I almost don't have to think. Yes, it's just going to kind of repeat the values again backwards. Yes? Cosine goes up and comes down. Then it goes up and then it comes down. Okay. So once I know the values, it's just going to kind of redo those values. Especially if what I'm plugging in is periodic itself. So if I'm doing every 1/8 of a pi step, I'm going to see that kind of pattern. So if I plug in 7 pi over 8, 7 pi over 4, where's that? Fourth quadrant. Right, so cosine of 7 pi over 4, now it's going to be positive 0.7, yes? And that kind of matches up with what it should do. It should go through, then back through. It's going to keep repeating those same things. Okay, so let's graph these here. Now that we have a much better graph to work with. Whenever our r is negative, I have to walk away. I have to walk backwards from where I'm looking. So here I'm going to look at 0 degrees, and I'm going to step out 1. I really should have scaled this. It's too bad, Jeff. Here, now watch. Okay, let me do this. You ready? Let me really, oh God. What's the largest output for R that we just got? And the smallest? Which makes sense because cosine goes between negative 1 and 1. So let's be really smart about this. Math is hard enough already. Let's make a scale. Just like the x-axis, do I have to go 1, 2, 3? Can't you go 2, 4, 6? Can't I go 0.51, 1.52? So I'm gonna call the blue line, I'm gonna call that 1. So then what's every step then? On the circle, what's every circle? Another what? 0.2, 0.4, 0.6, 0.8, 1. Do you see that? That's a choice you can make for yourself, dependent on how big your outputs are. Since my outputs are between negative 1 and 1, I don't want my graph to go, because then I'm like, what the shit is it doing? So let me just blow it up for myself before I start. So I'm going to call the blue line 1. So I'm going by 0.2s along here.
So at 0 degrees, I'm gonna go step out 1. Bam! And this is why I really like this graph paper, is because, well, shit, I forgot. This is, where would pi, yes?
I'm a little confused.
Oh, sure.
For the point sevens, right? Pi
Yep.
over 8, is it root 2 over 2?
Yep.
And that,
Is that cool?
it's
'Cause-
not just root 2?
No, okay. And again, the problem we just did a minute ago, where'd it go? It had a 2 out front, yes? The problem we did on the piece of paper, which is here somewhere, I had a 2 out front. So when the answer was root 2 over 2, it was multiplied by the 2 that was out front. We all know the cosine of 45 degrees is
Okay.
round 2 over 2. The one we just did earlier, I put a 2 out front, so it doubles. Yeah. Now what I'm just noticing is it has no pi over 8, but we're going to be okay. Where do you think pi over 8 would be roughly? Somewhere between pi over 6 and pi over 12, yes? Okay. We're going to make it. We're going to be okay. So I'm just going to go roughly, well, let's see here. This would be, what would it be, Jeff? 36th. Oh boy, that would be a 36th. I'm not going to think that hard. Just go right between the two. So I'm going to go out 0.7. So I'm going to go 1, wait, let's see, 0.2, 0.4, 0.6, 0.7. And then I'm looking at pi over 4, and I'm going to go out 0. Zero is really strange because you can't tell where you were facing if you go through 0, 0. I could have been facing anywhere because I just didn't go anywhere. So it's not a bad idea to start connecting stuff so you don't lose what's connecting where and when. So I know it's going to be like that. Let's see, what do we got next? We have 3 pi over 8, which is exciting. That's going to be between pi over 4 and pi over 2. So it's going to be between these two here. So I'm going to look this way, and I'm going to go how? Negative 0.7. Now, let me see. If I got to go backwards, that's a 12 and a 3, yes? All right, and I'm going to go between the two, yes? Which means if I go backwards, I'm going to go between the 12 and the 3 on the other side. So I'm going to look between these two, and I'm going to go out 0.2, 0.4, 0.6, 0.7. Then at pi over 2, I'm going to go negative 1. That's nice. Thank you, pi over 2. I'm going to go out negative 1, which is way back here. I'm going to look at pi over 2, and I'm going to go back 1. Five pi over 8, much like it did over here, it's going to be between the 3 and the 12. So I'm going to look at 5 pi over 8 here, and I'm going to walk backwards 0.7. So it's going to be a mirror image of this guy. It's going to try to be, poor little guy. So let's see, let's connect these. Look what's happening. Jeff, connected. There you go, buddy. And then if I look at 3 pi over 4, if I look at 3 pi over 4, which way how much do I go? If I look at 3 pi over 4, how far do I go? 0. Now, can anyone guess where it's going to go next? So it started here and it came through. Where's it going to go next?
It's gonna go back out.
It's going to go this way, make a leaf to go with that leaf. Do you guys see that? Because when it goes this way, it's going to make a leaf, and then when it comes back through, it can finish this other leaf. So I kind of have enough information now. I don't have to keep going with my table. I know what's going to happen. It's going to repeat that same leaf shape on the other side. And actually, I kind of got ahead of myself. It's going to repeat this leaf shape, and then it's going to repeat this leaf shape up here. So if it goes through this, and then it can complete this one over here. So it's going to be a 4-leafed rose. Yes? Okay. So let's see if we can do this a little bit easier. I don't have to continue with my table. I know it's going to have a mirror image point here over there. So between the 6 and 12, it's going to go out 1, 2.5. So between the 6 and 12, it's going to go out 1, 2.5. Then it's going to have a mirror image of this one. So let me stop for a minute. I really want you guys with me. The beautiful thing about these trig functions, they kind of repeat themselves. Once you draw maybe half the picture or so, you can kind of see where it's going to go. You're going to get a lot of mirror image points. I don't have to keep going with the table. So then this will connect. And then I'm going to have a mirror image of this guy down here. It's going to reconnect through. And then I'm going to have a mirror image of this guy up here. So it's going to be a point here. There's going to be a point between the 12 and 3 here. And then a mirror image on the other side. And then it's finally going to come through and complete this leaf over there. Okay. Yeah.
Why did you go out 0.5 instead of 0.7 on the third leaf?
I might have just miscounted. Did I miscount? 1, 2,
On the
3.5.
leaf on the left side.
1, 2, 3.5. It should be up here, yeah.
Okay.
Okay. That's just me miscounting. So it should be here then, yeah.
I was just making sure I wasn't missing something.
You're fine. You're fine. If you look on the other side of this paper, for example, yeah, this is kind of nifty. We did cosine of 2 theta. So if n is even, it has 2n leaves. And our n was 2, so we got 4 leaves. If n is odd, it'll start to kind of retrace leaves. So it won't be able to make 6 leaves if I put a 3 in there. It'll retrace the 3 that are there already. It just has to do with the period of the trig functions. Okay. So you've got the fan favorites. You've got the cardioid because it kind of looks like a heart, but it also looks like a butt. So you can call that the cardioid or the butt graph. That's fine. You have what's called a circle. And then you have this, what they're calling here, a clover. It's a little bit different than what we just did. It's got bigger, kind of like less symmetric in a way. Lemniscate is a nifty take. It's kind of like a circle, but you squared it. So it's more like one of these guys, but you squared it. These guys are the more interesting ones. And then you get all this other kind of stuff. So let me show you this. Last time I showed you guys or I think 2 times ago, I showed you the Etch-a-Sketch. So let me see if anybody reacts to, do I have it set on that? Yeah. Wait, don't. Okay.
Sorry.
So, has anyone ever seen this before? Okay. So in the days before the internets, even before Atari and shit, yes? In the old days, the olden days, we had Etch-a-Sketch, we had Spirograph, and this thing was my freaking jam. You picked a little gear to go inside, you had different sized gears on the outside. Do you see how it's all about the radius of this? Do you see how you put your pen in different locations inside the gear? So when you kind of like rotate the gear, your pen starts to trace out these shapes, yes? Now, I quickly found the old Spirograph one I used to do, which was really cool because it actually had the gears kind of moving around. It's not working anymore. So, but I found this one. Oh shit, I have stuff on it. I didn't want stuff on it. So you can change, do I want to? If you move these up, yeah, I'll do it. Let's see if I can remember what that is.
If you move this up and down, it changes the radius, which is effectively the same as choosing a different size gear from the game, from the spirograph. Okay, so each one of them controls each of the circles. The last one actually controls where your pen is. So right now my pen is there. If I move this last one up and down, it'll change where that is in the circle. All of those changes completely changes the shape of the end result. So if I do it the way I've got it set, and for some reason I want it set exactly like this, I get frenetic. Oh man, it's a little different now. It's okay, Jeff. Let me see if I can get it the way I wanted it. Is that too far up? That's closer. That's pretty good. Yeah, I think that's close. All right. Now the reason I wanted there is because I knew how to get this shape from my calculator. Yeah, there we go. So I can trick my calculator into thinking I made a change. Yes, it should be. So I have this for some reason. If you're trying to play along with me, make sure you set the theta max to be like 30. So 6 sine 3.15 theta.
What did you say for the max? 30?
Yeah, I've got it at 30, yeah. So real quick, just to show you, if I make this 0, 0, if I just make it 3 theta, we're gonna get that. And what it's doing right now, do you guys see, it should still be working. No, you're not working still. Oh, yes, you are. It's kind of retracing this over and over and over again. I really want this to make nothing but sense. If I do this, what have I changed? I've changed the what of the tree graph. Period. I've changed the period. So now it's not gonna, when it comes back around, it's not gonna line back up with itself. It's gonna be offset. And when I do this time, I get something very much like what I just got in the spirograph, yeah? So this is literally, and then it's just, all right, there you go. Everything you can do with this spirograph and more. Every one of these shapes has an actual equation associated with it because I could actually figure out the equation based on the radius and the pin placement of the gears. That'll change, there you go.
It's like
It won't
blue
stop.
circle.
Yes.
It's like a blue circle.
So the further off from a whole number this is, the freakier this gets. See how that's trying to oh, you can't see shit. Sorry. The further off, so I put it a little closer to be a full number 3. So it's going to try to trace itself over, but you see how it's just barely out of phase. So sort of every time it comes back around, it's a little bit out of phase. Yes? Okay. And if I just crank it up to, like, turn it off, Jeff, that's cranking it up, sure. If I take this to, like, 3.5, well, 3.5 is too far, 3.4. Yeah, now it's just going to go all over the place. And then you get, yeah, that's nice.
Sunflower.
I like it.
I might still have a spirograph.
Oh,
at home,
nice.
actually.
Well, I have my Etch-a-Sketch. I just have to order my spirograph now, and I'll be set. Okay.
I love those things. I used to bring
Play my
them
Etch-a-Sketch, my spirograph, and then my Oblivion remastered. Yes. Say again?
What was your table set?
Oh, the thing on the table that I was doing was not the table set, but the window. I was just making sure that I gave it enough room to kind of play with. I didn't want to make it stop at 2 pi, because then it wouldn't have like done all the out of phase stuff. Yeah? Okay. If I make this 2 pi, for example, I only get a little bit. Yeah. Okay. Okay. So, last new idea for the semester. So you guys have these if you need them. If I think about it, I'll throw some blank polar graphs up in Canvas. We'll see if I think about it.
Will you have any available for the tests?
Oh yeah. Yeah. I'll probably have them on the actual test. Yes? Okay.
Thank you.
So this is the absolutely the last new ideas for the semester, not forever, hopefully. This is section 10.4. And
one thing we do in 10.4, one of the first things they do things a little bit out of order, which is fine with me. We're going to talk about how to integrate a function of theta, yes? Now this is really important, especially those of you who are going to take 281. I think a few of you guys raised your hands. You definitely want to focus on this because this is going to be a huge part of my guys. We just did it like 3 weeks ago, I think we got into it. It's the three-dimensional part of what this is. So if I want to, here, I'm going to kind of truncate this little thing. So if I have this graph, and let's say I have part of this cardioid graph, yes? Oop, little butt graph. And I want to figure out the area here. Yes? Okay. We can do a similar thing to what we did with Riemann sums. When I say Riemann sums, what comes to mind besides? Oh, sure. Okay. I got that. Riemann sums. What shape comes to mind? Rectangle. Good. Because I have this thing here, and I've got these 90-degree axes, so a rectangle kind of makes sense to fill it in and estimate the area. Yes? And if we crank it up to an infinite number of rectangles, we get the perfect area as we go crazy. Okay, so what I'm going to do here is something very similar, but I don't have a rectangular coordinate system anymore. So I'm not going to use rectangles. I'm not going to use circles. I'm going to use little wedges. Little wedges.
Whee.
So that is the equivalent of one rectangle in a Riemann sum. Okay, I'm going to kind of truncate this a bit. Do you guys, now real quick. What is this? What is this? No, not that. What is this? How do I make that happen? If I'm here, how do I make it go, what do I have to change? Theta. That is d theta then, yes? That is d theta. Just like this was dx. And then I want to multiply that by, well here, let me just cut straight to the chase. This is d theta here. And if we take a step back in time, do you guys remember? Because what I effectively got is this. Yes, if I take this out and zoom in, I've got a pizza slice. Do you guys remember how to get the area of a pizza slice if I give you the radius and the angle? I want to know the area of this pizza slice. The angle looks like a pepperoni. So let's do this. This is one of the coolest freaking things. Somebody remind me, pretend like that's a normal little triangle. What is the area of this triangle? Kick-ass, yes? What is the difference between these two shapes? The bottom here is curvy. Do you all agree if I call this d theta, Jeff, you didn't have to write theta again, you already have it here. If I call it d theta, what would happen to this curve? Because d theta means I'm letting it be very tiny, which means I've zoomed way the shit in, yes? So then this is effectively straight. Now, does somebody remember the formula for the arc length? R theta. Very quickly. What the hell is a radian? I take the radius, I pick it up, I bend it, I put it down here. That's a frickin' radian. Radian literally just means one radius. So if I walk the length of a radius around my circle, that's one radian. Yes? So therefore, if I want to know how long this is, I would take the angle measure times the radius. If the angle measure is in radians, So 2 radians literally means 2 radiuses, 2 radii. So I would take 2 times how big each radius is to see how far that means. So of course the formula is S equals R theta. I'm really zoomed in, so this looks more like that. This is straight, but it's still R theta. So what is the area of this piece? R theta times? It's the base times the height, which is R. Good, so it'll be 1/2 R squared theta. So what's dA? 1/2 R squared d theta.
Why is R squared?
Area of a triangle is 1/2 the base times the height. What is the height of this piece? What's the height? How tall is it? R, because that's the center, that's the outside, that's R, yes? And what's the length of the base? R theta. So what is the area? 1/2 R theta times R, better known as 1/2 R squared theta. Okay. So one of my favorite derivations.
But that's only for
That's for the wedge.
this type of graph, right? Or is that for?
That's for any graph R is a function of theta. Because if I have something that's got a freakier edge to it, it doesn't matter. I would still just cut it up into these little wedge shapes. Every wedge shape would still follow this rule, yes? So that is the area of one wedge shape. So how do I get the area of the whole region? How do I get the area of this whole region? I would just integrate
Integrate it up to.
from whatever the first angle is to whatever the second angle is, yes? From whatever the first angle is to whatever the second angle is. I just add up all of those little pizza slices areas. Okay, maybe. So if I'm given R as a function of theta, and they ask me to find the area between theta 1 and theta 2, I would just calculate that. So let's try a concrete example out.
If you're taking the derivative of the whole angle, wouldn't it be just R d theta?
What do you mean? Sorry? No. So
We don't integrate, or we don't take the derivative of the R piece?
we didn't take the derivative of anything. I didn't take the derivative of anything. I don't blame you for thinking I did, but I didn't. So if I draw this a little bit cleaner again, if I take the little d theta piece out, yes? So then this represents an element of the whole area.
Mhm.
This is R. This is R d theta, yes? So then what's the area? It would be 1/2 the base times the height, 1/2 R squared d theta. I did not take the derivative of anything. I just put together little tiny elements of the angle, little changes in the angle. And I'm just, every time I move the angle by d theta, I get another little wedge, I get another little area, I keep adding. That's the whole idea of Riemann sums. I get a little tiny rectangle, I get its area, and then add it to the next little tiny rectangle. Now I just have these wedges. Because my system isn't rectangular anymore. It's circular, so I gotta use these little freaking pi wedges and add those up. It's exactly Riemann sums. Just with a different shape. So it's really on one level it's kind of nifty to see the influence of the geometric formula for the shape that I've cut it into come into play. That happens in rectangles. Why does the interval end up being f of x dx? f of x was the height, dx was the width, yes? Boom. So why is this the way it is? Because that's the frickin' area formula for that shape. Yeah. Okay. So let's try an example. Yeah, here we go. Okay. So let's say I want to find the region, find the area of the region between r equals 3 sine theta and r equal 1 plus sine theta. This question should kind of feel familiar from 180. When I had to find the area between two functions, does anyone remember the very first thing you needed to do? I wanted to find the area between those two functions. Find where they intersect. Is that what you're gonna say? I appreciate that. That was exactly what I was saying. How do I find out where these two things intersect?
Set of equal to each other.
Holy shit, so what would you get?
I mean, set up the equation. So I'm going to make r equal r. So what do I get? 3 sine theta? 1 plus sine theta. Okay. How the shit do I solve that thing?
Put the sands.
You're like, I don't know, man. Put the signs on. I love it. Algebra should kick in now, right? Trying to solve for theta. I'm going to get all my theta stuff on one side, yes? So, what do you get when you do that?
Minus sine, 2 sine. Okay, it's looking better, looking better. Divide by 2. Kicking the ass in.
Why is it 2 now instead of 3?
Because what's 3 things minus 1 thing? Okay.
Yeah. Sorry. Sorry. Okay. Now, don't do inverse sine. Holy shit. Just what angle makes sine 1/2? What's one of the angles? One of the basic angles that makes sine 1/2. Sine likes y. If you want it to be small, it's got to be far away from y. It's got to be close to the x-axis. 5/6. Yeah.
What else makes it 1/2? It's positive, yes? So if it's in the
5
second
pi?
quadrant, yes, 5/6.
No, that's all I need. I don't have to go any further. That's where those two intersect. I could rewrite them in like coterminal, add 2 pi telegram. No, why would I do that? By the way, can you guys tell me,
What shape does this have? Centered on which axis? Y-axis, because it's sine. So it's like there's a circle here, and then this one is a circle that's been shifted. Believe it or not, it's not a circle. If you look at your where did I put mine? There it is. If you look at this, how do you get a cardioid? Well, they don't tell you all the ways here. That kind of sucks a little bit. Cosine makes a butt graph that's on the x-axis. If I made this sine, that would be a butt graph that's on the y-axis. And do you see how it's 1 plus sine? This one's half, but mine will just be twice as big. You got a big old butt. So this is going to look like, here, let me just show you. There's my circle. There's my cardioid. Those are the 2 angles where they meet. So if I gave you a problem like this, I would give you the graph so you can kind of see where things are happening. You still have to do the algebra and the trig to figure out the numbers, but you can kind of see where you can stop. So how do I set up this integral then? So in general, it's 1/2 r squared d theta from theta 1 to theta 2. Jeff, it's not a cube. It's still not a cube. Okay. So this would be 1/2 what to what? 5/6 by pi/6 r squared. What was r? Yeah, 3 sine theta, so it'll be 9 sine squared theta d theta. Now, does that look familiar?
Not specifically familiar, but just what you're gonna have to do. It's got sine squared inside. Does anyone remember how to actually integrate that? Now we're back in chapter 7. Right? You have to use a certain identity. Yeah, exactly. It's related to half angle. It's called power reduction, but it's just half angle formula reformulated.
So I'm going to pull the 9 out. How do I rewrite sine squared? 2 theta. That's the whole idea. It's related to half angle, so it's just backwards. So then I,
Instead of cutting an angle in half, a double angle on the other way. Yeah. Okay. And then we can integrate that relatively easily, yes? Yes, okay.
that's not a horrible one. I'll just pull the 1/2 out, make it 9/4. Integral of 1 is theta. What's the integral of cosine 2 theta?
Negative 2
Nope.
sine.
Not the derivative. Since you're integrating, you have to kill the 2 that would want to come out. Yeah. Okay. And then you just plug stuff in. Okay.
So this is the first little mini step into this idea. There are x and y equations that would capture the same graph. Do you understand that those equations would be disgusting? If I wanted to get this graph using x and y, do you all agree that would have to be absolutely horrendous? So this is a broad idea in mathematics. The more coordinate systems I know, the more I can try to find one where my current problem is easier to do. What's the equation of a circle in xy?
Square equals y squared equals r squared.
What's the equation of a circle centered at the origin in polar? Radius 3. R equals 3. That's the equation. So if I have things that are kind of circular in nature, doesn't have to be perfectly circular, I'm going to want to convert to polar, because then all of my work should be a lot easier. The equation should look better, which should lead to easier integrals and derivatives. So if you're going to take 281, one of the beautiful things you're going to do is you're going to start to learn other coordinate systems. And you're going to see some old problems that become really relatively easy if you're allowed to use a different coordinate system. It's a generally beautiful idea in mathematics. If it's disgusting to do algebraically, I'll do it graphically. If it's hard to do that and it's hard to do with xy, I'll try r theta. If r theta sucks, I'll try something else. How many other coordinate systems are there? I have personally used about upwards of 20 something. There are a lot of coordinate systems. A lot of them are like little tweaks on major ones, but there's a ton of coordinate systems. Yes?
So this may be a dumb question. I don't know like if I'm thinking about it wrong, but didn't we have 2 values for r for this?
Oh, yeah.
So why did we choose 3 sine theta instead of 1 plus sine theta?
Oh yeah, okay. I completely forgot that this guy was even here. I thought this guy was everything for a moment. That's my fault. It should just be the difference of these two then. Yeah?
So
You would do, this integral we did is beautiful. I love it. This integral is awesome. And then you do the whole thing again for this guy. Yes? You would plug this in for r,
okay.
and then you subtract the 2.
Okay.
And that's my
Okay.
fault. I
Okay.
totally,
I was
for
like-
some reason, I just thought it was just that. I forgot what I'm sorry.
I thought that I was like going
No, you're fine,
crazy.
you're fine.
but
Just
I
like
didn't
in
know.
180, when you had to find the area between 2 functions, then you do the integral of one function minus the other one. The trick with this, since I have to do r squared, you actually do have to do what I just did. I'm not gonna try to pretend like I did it on purpose. And then you would subtract the integral of the other one. So you'd end up with the area between the 2, yeah?
How do you decide which one goes first?
Oh, the same way you did in, so real quick. We know these meet at pi over 6 and 5 pi over 6, yes?
Uh-huh.
Do you all agree that pi over 2 is between those?
Yeah.
If I plug a pi over 2, whichever one is bigger will be bigger the entire time.
Okay.
So that's how you always figure out which functions on top is. If you know where they meet, whatever the relationship is at one point between, that's got to stay that way the whole way through. Yes? So pi over 2, this will be 3, and this will be 2. So this guy is on top. So it'll be this guy minus this guy. So you would do everything we just did is great. Good job, Jeff. And then you do everything we just did again for this guy and subtract the 2. And then you look at the area between the 2. Yeah. Okay. And I apologize, guys. I don't know if I've ever been as tired as I am right now. This week has really taken it out of me. So I know I've made some mistakes and I'm really sorry about that.
Don't worry about
Sweet, thank you. Give me a little grace, I like that. Here's something that will definitely make it up. As much as you might hate me even more after I've made mistakes, somebody picked up on this too early. I'm gonna make 10-4 extra credit. I highly recommend, more than that, if you like yourself at all, and you're gonna take 281, you're gonna do 10-4. You're gonna get that damn extra credit, yes? If you're not going to take 281, I'm okay with you not doing that, right? If you're not going to take 281, you're not going to have to do like the next level of this, and I'm okay with you not getting more practice with this. Okay. So somebody picked up on the fact that there's no 10-4 stuff on the practice test, and I was like, damn it, be quiet, because I want you guys to pay attention when I was talking about it. Let me think. I think that was everything. Yeah. So, if you have any questions, let me know, but we could certainly call it a night there. You've got the practice test, so I'm going to bring the answer key next time. Yeah.
Is 10-4 like what we're doing right now with the area between?
Yeah. Yeah. Obviously, some of the problems get a little bit trickier.
Yeah.
That's a very basic problem. Yeah.
I haven't looked, I'm not sure if you have or not, but are you gonna put the 10-4 homework on the website?
Oh, I need to.
Okay, I just wanted to make sure because it's extra credit, so I didn't know if it was
Yeah, you guys still get a chance to do it.
perfect.
Yeah.
Thank you.
Mr. Waller.
Oh, there's. Did you get yours? Yeah, you did. No? You must have. I forgot to change the date. Here's yours. I'll just date it. Maybe. I don't know if I've ever been as tired as I might have given yours away, Steph. Which doesn't make any sense, but, or it maybe, this is why I thought I missed Paul's, is I thought maybe it was still in my printer. Because maybe my printer ran out of paper in the middle of printing. So
Mine
if
comes
you have
after.
if you have a moment, I can go print it back out. Yeah, if you have a moment.
Yeah, I would like to know where I stand.
Huh?
Talk to me.
Yeah, alright, come with me back to the office. I'm gonna go and die for a little bit.
How much longer do you have to stay here?
Today I don't.
Because I see you a lot of times, you go back to your office and then,
Oh, just to upload the video. And then I'm out. Yeah.
Did I get that?
Where did I put my? That's the evil thing about glasses. You need to wear them to find them. Okay, great. Okay. Oh, you know, you can't plug infinity in this. So this doesn't really have a meaning. It's the oscillatory nature that you have to figure out. Yeah? As the inputs will always be multiples of pi over 2. So the outputs will always be 1, 0, negative 1, 0, 1, 0, negative 1, 0. So it never actually, the limit is not 0. Limit not 0 does not mean infinite, right? In this case, this is oscillatory nature, so it's not 0, but it's not infinite. It just doesn't ever kind of like agree to stop moving. Yeah.
And then except for,
3, yeah, yeah.
Okay,
I was just
I got
saying,
that.
that's the way you write this limit
Oh,
equals
okay.
infinity. You can't take infinity times something.
okay.
You can't plug infinity into sign, right?
Right.
That was this, yeah. You can't do that kind of stuff with infinity. The answer to a limit can be infinity, because the answer to a limit is what it's approaching. So that's fine to say that's equal to infinity, but you can't plug infinity into something. Yeah.
Just real quick, so I missed last 2 classes, and I was gonna ask, like, I'm in it, and everything's kind of like very digestible. So is there anything like kind of like big that I should go over on YouTube?
So you missed the last 2 classes. So that's all of chapter 10. So we did parametric, and of course we did polar. If you remember parametric pretty well, it's nice. The calculus for parametric is really pretty straightforward.
Yeah.
Right, you can look that up. Dy dx is just dy dt, dx dt.
Yeah.
Just that ratio. It's pretty straightforward. If you remember your parametric,
Yeah.
you're right where you want to be.
Gotcha.
Yeah,
Okay.
because a lot of it was just reviewing parametric.
Yeah.
Yeah.
And then I was able to get my test.
Oh.
Romero, basics.
Yeah.
I did get that sheet back though.
Yeah, you did. I just don't have your test here. It had another stack. Here we go. Oh, here we go.
Thank you, guys. I was worried I had somebody. Okay.
Since you said 10-4 section 30, is that in the homework section for 10-4? Okay, since it's not on the sign, if we wanna do it.
I just need to put it in. The last time I put stuff in was right before class, and so I had to, it got to 10:03, I'm like, I gotta do it.
Okay.
So I didn't leave it on purpose. You guys all have a chance to do it, just gotta remember that. So if you think to email me,
I will.
by the time we get home tonight,
Yeah.
I'm probably gonna forget, so,
I get that.
thank you. Alright, Steph. I can never just leave somewhere.
I feel like I could give impulse hope.
What do you mean?
I don't know.